Okay, I think we can start. So thank you very much for being in the session, both the speakers and the attendees. And okay, we have some more. That's nice. Okay, so we're going to, our first speaker is Takayuki Nozawa, who is going to present multi-scale performer, audience, physical synchrony in joint music performance. Very interesting.
Thank you very much for introduction.
The floor is yours.
Let me share my slide. Can you see this?
Yes, I can see this. Yes, I can go to proceed. Yes.
Great. So I'm Takayuki Nozawa from Tokyo Tech, Japan. And the presentation title is Multiscale Performer Audience Physical Synchrony in Joint Music Performance. And this is a collaborative study between Tokyo Tech and Guildhall School of Music Drama and Imperial College London. So these are the contents of my talk today. First, let me explain the background and purpose. In various types of communication and interaction, interpersonal physical synchrony is highly connected to their generally positive experiences. In the context of classical music performance in particular, physical synchrony between performers has been investigated, revealing its association with leadership and improvisation and so on. However, previous studies rarely investigated the possibility and also the meaning of physical synchronization between music performers and audiences, or as I call peer sync, because in the context of classical music, audiences are supposed to be passive and static. In classical music, common performance practice is to follow the score in a very strict and accurate manner. But on the other hand, a more creative and improvisatory approach is now gaining attention, as it is suggested to enhance musical experience on both performers and audiences side. So we call the first approach as the strict mode, and the second approach as the let go mode. And comparing this let go with strict performances is a reasonable method to manipulate collective musical experiences while controlling other factors. Thus, we conducted an experiment focusing on the performer audience sync in the let go and strict performance modes, and along with the audience's subjective perception of the performances. We had three specific hypotheses. First one is that the let go performance would be perceived by the audience as more innovative than the strict performance. And second, let go would induce a higher performer audience sync than the strict. And third, the audience's perception and peer sync would be positively correlated. So we checked all the relationship between these three components. Now the experimental method. Music performers were this Portoria string quartet, and for the audiences, out of around 50 people, actually 42 audiences cooperated on the measurements throughout the experiment and provided analyzable data. So we use the data from them. And here is a snapshot of the experiment conducted in the Guildhall School of Music and Drama. And the quartet performed the same pieces by Mozart and Haydn twice, each with let go and strict modes. They actually also performed 4 improvisation pieces, but those were not used in the current analysis. So I hope you can not see, but also hear this. Here is a video recordings of the same piece by Mozart with let go and strict. So please try to figure out which one is let go and which one is strict.
I think we cannot hear the sound. I don't listen to the sound.
Really,
perhaps it's on the sharing of the screen that you must do something.
I see.
When you do share the computer sound or something.
Okay, I'm sorry. I'll replay it if I had the time later. So I'll go on. And for the physical measurement, the performance head motions were measured with inertial motion sensor on their forehead, like this, pressed like this. And the audience's body fluctuations, spontaneous body fluctuations were measured with a smartphone that were worn around their neck like this. And after each 2 performances, audiences rated their subjective evaluation of each performance on these 5 items: improvisatory, innovative, emotionally engaging, musically convincing, and risk-taking. And the effect of let go versus strict was tested on the group level tests. And for the PS-Sync, first the acceleration data of the performers and audiences were converted to the norm time series, like this. And then for each performer audience pair, synchrony was calculated using wavelet transform coherence. And for each time segments corresponding to the music performance, the wavelet coherence value was temporarily averaged at each time scale, and then averaged over the 4 performers. This gives us the PA-sync value for each audience for each performance. And on the group level, the effect of let go versus strict was tested at each time scale. Now, I'm moving to the results. First, these graphs show the audience's perception of the different performance modes. That means let go versus strict on the 5 rating items. As you can see, let go performance were rated to be significantly more improvisatory, innovative, emotionally engaging, and risk-taking than the strict performance.
Mm-hmm.
And now here is the main result of this study. So interestingly, the comparison of PA-Sync synchronies represented in this graph on the vertical axis. And PA-Sync showed opposite effects depending on the time scales shown on the horizontal axis. So in the shorter time scale, like here, strict performance modes actually enhanced larger performer audience synchrony. But in the longer time scale, like here, let go performance mode enhanced larger performer audience synchrony. And we checked the direct association with the PA-sync in the shorter time scale with 5 ratings. And we found that PA-sync in the shorter time scale was negatively correlated with the improvisatory, innovative, and risk-taking ratings. And doing the same analysis on the longer time scale, which showed the let go enhancing effect, we found that the PA-sync in the longer time scale was then positively correlated with the improvisatory, innovative, and risk-taking ratings. And now we discuss the results. On hypothesis 1, audience perceives the let-go performances to be more innovative than the strict performances. So this supports that the manipulation of performance modes successfully induced the differential musical experiences on the audience side. And on hypothesis 2, as expected, PA-sync succeeded in differentiating the let-go versus strict performance modes. However, the effect of mode was opposite depending on the time scales. In the shorter time scale, actually let-go performance diminished the PA-sync. But on the other hand, the let-go synchrony dominated strict synchrony in the longer time scale. This is in accordance with our expectation. So these results suggest that the collective musical experiences embodied in not a unimodal but a multi-scale dynamical adaptive process. And in the shorter time scale, higher PA-sync was also negatively associated with the audience's subjective perception of innovativeness. So this suggests that the shorter scale synchrony may actually reflect the automatic and unconscious alignment to the low-level music structure. What I mean is the more standard and predictable performance was, the easier it may have been for the audience to physically get entrained into it. On the contrary, higher PA-sync in the longer time scale was positively correlated with subjective experience of innovation, innovativeness. So it may reflect that the longer scale synchrony is representing the engagement, audience's engagement into the dynamics of higher level musical expression, which was enriched by the let-go performance mode. In conclusion, collective music experiences embodied in a multi-scale, not uniscale, but multi-scale dynamical interaction process between the performers and audiences. And furthermore, this multi-scale physical interaction was sensitive to the creativity involved in the music making. And furthermore, the result supports the utility of physical sensing technologies in capturing subtle but important aspects of collective music experience. Yeah, that's it. Thank you for listening.
Okay, thank you, Takayuki, for a very interesting presentation. We have some time for 1 or 2 questions. Are there any questions? I think it would be interesting to analyze your time series also with other methods, because we are doing some time series, and I think you can find some results with other analysis tools like complex network analysis or things like that. So it would be very interesting, I think, from what you have shown us to do something.
Thank you very
like
much for
this.
suggestion. Yeah. We are definitely going to look into, for example, the spatial distribution between the propagation of synchrony could be interesting topic.
Spatial and temporal would be very interesting. Okay. So is there any other question? If not, thank you again. And
thank you very much.
We pass to the next presentation from Makoto Takeuchi, if I pronounce well, with entitled Burstiness in the Physical Activities of Children and Adults.
Yeah, I have a pre-recorded presentation, so share my screen. Sorry. Wait. One more time. Yeah.
Yeah, try the sound, see if we listen to this. Yeah, it seems something.
Hello, my name is Makoto. I'm a PhD student at the University of Tsukuba. Today I'll talk about burstiness in the physical activities of children and adults. Let me start with a question. What is the difference between the behavior of children and adults? For example, these differences are expected, but we don't know. So let's check the real data. The following are 10-minute physical activity event sequences of a child and adult during a day. Here, the vertical lines are shown at the time of action. Which one is a child sequence and which one is an adult? The answer is this, but we cannot tell the differences in appearance. So our question is this. Is there any statistical difference in the behavior of children and adults? If there is no difference, then the behavior of children and adults may be governed by the same constraints that are independent of body and brain growth. On the other hand, if there is a difference, does it arise from differences in the behavioral principles? So, this is the outline. The burstiness is intermittent, increases and decreases in the activity or frequency of events. The burstiness has been reported in various human behaviors and represents inhomogeneous behavior. Burstiness is explained by various models, such as skewing model. Intermittent times are intervals between consecutive events. If there is burstiness, i.e. this distribution has a fat tail, such as power law. For human burstiness, universality class is reported. On the other hand, there are also studies that focus on differences of power law exponent. This seems contradictory, but it may be due to differences in targeted behavior and observation method. An individual's burstiness may vary depending on his attributes and conditions. So, in this study, we analyzed the burstiness of physical activity in children and adults. Next, our data and method. Let's talk about the data. We study physical activity as measured by accelerometers. Activity data for about 3 hours during the day for children and adults, and about 30 minutes during the day for an infant. Infant's data is short because we only use the data when parents don't touch her. Children were measured while playing, and adults were measured while at their desks, talking, cooking. Our dataset includes 2 children, 3 adults, and 1 infant. Pre-processing of data is this. The acceleration time series data is collected and transformed into activity data, which is then transformed into event sequence data with individual specific thresholds. Next, we calculate the statistical features. For burstiness, we check the distribution of IETs and power law exponent alpha and burstiness B. Precisely, we use the Bn collected for the number of events. Next, for temporal correlation. Just to be sure, we checked several types of features. Without going into detail, power spectrum is calculated the Fourier transform of autocorrelation function. Thus, theoretically, the Bursty train size distribution decays exponentially when there is no correlation in the IETs, so the correlation can be confounded by the deviation from the exponential decay. So anyway, let's show you the empirical results. First, how are IET distributed? Here, IET's cumulative distribution are plotted in log-log scale. Adults distribution has fat tail, and children's distributions have more fat tail. That means smaller power law exponent. And in the case of infant, the distribution looks like it has exponential cutoff, but short observation time could make it seem so. The table shows the result of estimation of alpha, and the minimum tau is the lowest value of IETs following a power law distribution. Next, how individuals are plotted on burstiness and memory plane. This is a two-dimensional plot of P and M for various event sequences, as reported in the previous study. Our result is this. Children have higher burstiness than adults. This is consistent with the IET's distribution mentioned earlier. And infants have lower burstiness than adults and seems to be close to natural phenomena. Next, how are power spectrum distributed? These are power spectrum of a child and an adult that show 1 over F noise. Note that this is one individual's data per graph. Does it come from IET's distribution? When the value of IETs are independent from each other, the scaling relation determines alpha omega as follows. So, we randomly shuffled the order of IETs values while maintaining the frequency. Then, alpha omega gets smaller. In other words, it gets closer to theoretical values. Therefore, the original IETs are correlated, which affects the alpha omega of 1 over F noise. And infant has a peak that is almost unchanged by the IET shuffle. It is unconfirmed whether this peak generally represents the characteristic of infants. Finally, to make sure, we also check the temporal correlation in the Bursty train size distributions. In these graphs, the horizontal axis is the Bursty train size E, which means the number of events a single Bursty train has, and the vertical axis is its probability density. In 1 to 5 seconds timescale, consecutive IETs are correlated because they appear to deviate from exponential decay. And correlations longer than 5 seconds cannot be confirmed due to lack of data. So let's move to conclusions. First, IETs of children and adults have different distributions, and it might be explained by a model that generates different IET distributions. For example, position-based priority rest model has been proposed. Interpreted by this model, the priority of physical activity and rest or mental activity not involving physical activity differs for children and adults. Second, IETs have temporal correlations in physical activities. That means not generated from the linear process. The temporal correlations may be explained by the mechanism of self-excitation, such as the Hawkes process. Finally, in our data, the behavior of infant differs from that of adults and children. This is interesting, but further data collection is needed. At last, we would like to mention future perspectives. We will acquire more data and validate the models that can generate it. It would also be interesting to get activity data and vital data, such as heart rate, at the same time. That's all. Thank you for your attention. Thank you.
Thank you very much, Makoto, for your very interesting presentation. I have seen there is a question, but that has been answered in the chat. Is there any other questions to the speaker? Okay, Makoto, did you try to see perhaps the time series of the intervals between the activities?
Sorry, one more time, please.
Yeah, I will repeat. Did you try to see, for example, how evolves the time series of intervals between actions?
Chat in type in chat.
Okay, okay, sorry.
Thank you.
I don't know if it is clear.
Yes.
If you take the intervals. Or
yeah, intervals. Yeah. I check the intervals.
Oh, okay. Okay. Is there any other question to the speaker? Okay, so thank you again, Makoto. We pass to our next speaker, which is Federico Botta. with the title of his presentation is In Search of Art, Rapid Estimates of Gallery and Museum Visits Using Google Trends. The step is yours, Federico.
Thank you. I'll share my screen because I have it pre-recorded. Okay, so I'm going to start now. Hopefully you'll be able to hear the audio, otherwise stop me, please. Every year, hundreds of thousands of people visit museums and galleries across the world. In the UK, they might go and have a look at the paintings in the National Gallery in London, or they might go and have a look at the more contemporary and sometimes controversial art, which is available at the Tate Modern Gallery. Or they might look at the natural wonders available at the Natural History Museum, like this dinosaur. In the UK, the Department for Digital, Culture, Media and Sport sponsors a range of museums and galleries, meaning that they are free to enter, which of course is great. But this poses challenges for the museums and the department in terms of knowing how the museums are performing in terms of visitor numbers. So each museum collects data differently on how many visitors they had in the previous month, and then this data is collected and aggregated and released by the Department for Digital, Culture, Media and Sport, which from now on I will be referring to as DCMS. So in this project we worked with DCMS to try and help them have a better understanding of how the museums are performing, which is something which is of interest to them and in general to cultural policymakers. So DCMS releases the data on the number of people visiting the museums and galleries on their website, so that's publicly available. Until recently this was released on a monthly basis, now it's quarterly, but in this project we worked with monthly data. So the data is released by DCMS on their website, but it's released with a delay. So for instance, if we were looking at, back in 2018, for instance, if we were looking at data for August 2018, so how many people visited the museums and galleries sponsored by DCMS in 2018, this was not released until 4th of October 2018. So there was a delay of just over a month, which sometimes poses challenges for cultural policymakers who would like to have faster estimates, so faster access to the performance of the museums, so that they can take prompt actions to address any issues that might be arising, for instance. So in collaboration with DCMS, we tried to work with them to see if we could generate earlier and accurate estimates of how many people are visiting the museums and galleries on a given month. So if we look at an example, for instance, let's take Tate Modern, and this is the number of monthly visitors over the last 10-15 years, and you see that there are some clear patterns. So summers are typically busier, so in July and August there's typically more people visiting the museums such as Tate Modern. So a very kind of naive and very simple approach to estimate how many people will visit the museum, say, in a specific month of a year, would be to assume that it's going to be similar to the same month from the previous year. So for instance, we could think, okay, August 2014 is going to be giving us a good indication of how August 2015 will be, because Augusts typically are higher. But this is not, of course, always the case. It's a very simple approach, looking at year-on-year change, and this doesn't pick up, kind of changes that happen throughout the year. For instance, August 2015 was significantly lower because of, I think, partial closures of Tate Modern that year. So in fact, if we do this very simple naive approach over the whole year, we get a very large percentage error of about 41%, which is far from ideal. So of course, this, as I said, a very kind of elementary approach, which doesn't take into account really many of the properties which are in our data. So if we look at the data from a more statistical point of view, so we look at a time series perspective, so we can construct different time series models, say for instance an REM model, which picks up things like the trend in our data, picks up the seasonality in our data, and so on. These of course will pick up more of the patterns in the data, and in fact if we do this, we reduce the error already to 23%. So if we generate monthly estimates using an REM model, we can reduce the error already. But what we thought was that we could do better than this. And in particular, what we thought was, well, can we use our online information gathering process to actually better understand the interest in these museums and galleries, and the interest will be an indication of how many people are going. What do I mean by online information gathering process? Well, if you are, like me and like many other people, if you want to go to, say, Tate Modern and you've never been, you might want to know where it is. You might want to know how to get there, so what bus stop or what tube line you have to get. You might want to know what the opening times are, or you might even want to know if there is a special exhibition on. And chances are that if you want to find out any of these things, you're going to use Google. So we looked at the search volume of for a specific museum or gallery, in this case Tate Modern, on Google, and tried to say if this could help us generate better and faster estimate of how many people visited a specific museum or gallery in a given month. So Google provides this data by the interface Google Trends, which provides an index which is proportional to the search volume for a specific topics, in this case Tate Modern, over a period of time. So for instance, this is from early 2004 until present, and we get data on a monthly basis. And what we do is we construct a time series model, so for instance an ARIMA model, which not only is trained on historical data, so on how many people visited the museum in previous months, but also on uses how many, the search volume for the specific museum, again in this case Tate Modern, over the past few months as well, and to enhance our simple ARIMA model. So for instance, we looked at all the museums sponsored by DCMS, but here, for instance, I'm going to show 3 examples. So Tate Modern, National Portrait Gallery and Science Museum, and on the y-axis you have the monthly number of visitors, and then on the x-axis you have the search volume of Google as provided by Google Trends. And you see that for some museums it works better than others, but this is a simple kind of scatter plot. But what we actually did in our analysis was slightly more sophisticated. So if we look at the top row here, what you have on the x-axis is the training window, so the number of months that we use to train our ARIMA model. I'm focusing on the top line here. So we select a number of months, say 30, that's the lowest that we pick. So we pick 30 months of data, we train an ARIMA model, both with and without Google data. So the pale red line is without Google data, and the dark red line is with Google data. And we train an ARIMA model, we generate then monthly estimates by shifting our training window by 1 month each time, retraining the model in an adaptive manner, and generating estimates for, I think, about 8 or 9 years. And then we calculate the mean absolute scaled error of these estimates. And what we find that across all training windows and across all the museums, models which include data from Google Trends perform significantly better than models that do not include data from Google Trends. So for instance, if you look at Tate Modern, which is a very good example, the model which includes Google Trends data has a significantly lower error than a model which does not include Google Trends data. And this holds across the various museums. And in fact, to further validate this result, we have also performed a statistical test to compare the forecast accuracy of the various models. And what we have used is the Diebold-Mariano test, which is a test to compare the forecast accuracy of time series models. And this test does confirm that models which include Google Trends data perform better in terms of the mean absolute scaled error compared to models that do not include Google Trends data. Then the next step was, well, okay, we have shown that this works, we've shown that we can generate better and more accurate estimates using Google Trends data, but we have done this using an ARIMA model, which is one of many potential ways of modeling this data. So are our results specific to the fact that we use an ARIMA model? So to address this potential issue, we also looked at using neural networks. So that's what you can see on the bottom row of the plot. So we used the neural network autoregressive model, which is simply a neural network for modeling for the time series and generating forecasts. And again, we did exactly the same analysis, so different length of training windows, and a neural network which included Google Trends data and a neural network which didn't. So in the pale blue line is a neural network which does not include Google Trends data, so it's trained on historical data alone. And at the bottom one, so the dark blue line is a neural network which includes Google Trends data. And again, we find exactly the same results as with the ARIMA model. So models which include Google Trends data perform better, so give estimates which are more accurate compared to models which do not include Google Trends data. And again, we validated these results using the Diebold-Mariano test for forecast accuracy as well. So this is very encouraging. In fact, we have shown, we have been able to show that models which include Google Trends data give us more accurate estimates. Because Google Trends data is available for instance, for a given month, say we are looking again at August 2018, for instance, Google Trends data for that month is available as soon as that month is finished. So on the first day of the, say, of September, we would be able to generate our estimates because we would have the whole month of August search volume coming from Google Trends. So we can generate estimates on the first day of a new month, which is a month earlier than DCMS releases their data to the public. So this is great, but there's a final piece that we wanted to test and validate. So far we have shown that we can use a keyword, so for instance Tate Modern, to better estimate how many people visit Tate Modern in that month. So we've shown that these two things are correlated and improve our estimates. But what we wanted to further validate is whether we can use any keyword coming from Google Trends which is related to the UK or London to improve our estimates. Because if that is the case, then it kind of indicates that it's not the specific keyword related to the given museum that contains information about the number of people going there, but it's simply the fact that people are more interested in going to London, going to the UK, and so on and so forth. So what we did was we picked some, in fact, 8 control topics. So for instance, if you look at the bottom right plot, we picked the topic United Kingdom. So what we did was downloading from Google Trends the search volume for the topic United Kingdom for the period of time corresponding to our analysis. And we did exactly the same analysis as we've done with the museums keywords earlier. So we tried to generate estimates of monthly visitors to a museum using the search volume not for that museum, but for United Kingdom. What happens is that the model, which includes Google Trends data, in this case, does not perform significantly better than a model that does not include Google Trends data. And this is true across all the 8 control topics, which range from, some that are clearly related to London. We used, in fact, London or Buckingham Palace or Hyde Park, and some which are slightly related, like England or United Kingdom, to topics that are completely unrelated, like travel or color. And across all of these control topics, using keywords which are not related to the specific museum or gallery under study does not improve the estimate generated. And this shows that the specific term, search term that we've used, specific to a given museum, contains valuable information on the interest or the people have for that museum, which is related to how many people visit the museum in a given month. So more broadly, our analysis has shown that we can use what people search for online to better estimate what people are doing in the real world, and crucially, we can do this in near, real time, in the sense that we can remove the delay that, for instance, DCMS currently has in releasing these data, which are useful for cultural policymakers in general. So we can provide faster access to the current state of society, in this case measured as the performance of a range of museums and galleries. So these results have been published earlier this year in EPJ Data Science. So if you're interested in reading more, you can also have a look at the paper, which is linked here. And thank you very much for listening.
Thank you, Federico, for your very interesting presentation. Are there any questions, Federico?
Thanks.
So I would ask a question. If I have seen well, Federico, the performance is different depending on which museum you are looking for. Am I correct?
Yes, so that is correct. For some museums, it works much better than for some others as an overall performance. But what we were interested in the paper was, regardless of the kind of baseline performance, can we improve that by introducing Google Trends data? So yes, for some museums, in general, the performance is better. But what is true is that for all museums, if you include Google Trends data, the accuracy improves. But where the accuracy kind of baseline value is dependent on the museum.
Okay. Do you have any idea why is this, or if there is something for future research?
Yeah, I mean, it's challenging. So there could be different reasons. One is, one that comes to mind is that some museums are part of. So it depends on basically on how people search for these museums on Google. So for instance, if you think of the Tate Modern, it's part of a bigger group of museums, which is called the Tate Group. So then depending on how people search for things on Google, that might affect the performance. And then in general, the baseline performance is also affected by how each museum collects the data on the number of visitors, because this is not standardized, and some museums collect it by sensors at the door. and sometimes some other pieces do it differently. So there is also an intrinsic error in the kind of ground truth data that we're using.
I see. Thank you very much.
Thank you.
Is there any other questions? Okay, so let's thank Federico again, once again.
Thank you.
And we pass to our last but not least speaker, which is Adriana Correa.
Hi.
Who is going to present something from physics, reminding physics, putting a spin on language, a quantum interpretation of ambiguous sentence readings. Very intriguing. The floor is yours.
Hello, I have a pre-recorded presentation.
Okay.
So I am going to share my screen and hopefully everything will work out. Can you see it? Hello, everyone. Welcome to my spin on language. I'll be telling you about my PhD research that I'm conducting at Utrecht University. So for starters, I'd like to tell you about the current state of natural language processing and what it is happening right now in the field. So right now, huge language models that learn using machine learning are being fed huge amounts of data, of words, of sentences, and they're basically learning statistical patterns from the sentences that they see, that they observe. And that is very costly, although it has given some really impressive results. Recently, there was an immediate GPT, and it was quite impressive. But it also gives rise to some very funny and interesting situations because it really doesn't understand what it is doing. I have this example here from a recent paper that gave a prompt to GPT-2, where it asked to complete the sentence 3 + 5 =. And funny enough, according to the authors, this is quite a good sample of the answers that it was giving. So it was not cherry-picked. Some examples that I like are 6 if it does it again, and 5, and then lots of expletives, and this one equals 10, watching this case, etc. And then it stops abruptly. So it's not perfect at all. So how can we introduce point? And how can we use what's done already, which is not nothing, to get a yet better model? For this, we will start with the idea of compositionality. And we can observe that when we read a sentence or hear a sentence that we've never seen before, heard before, we will understand what it means. And that comes because we know what each of the individual words mean, and we know the order in which they come, and that means something to us. What is that exactly? So according to Frege, in his principle, the meaning of a complex expression is determined by the meaning of its constituent expressions and the rules used to combine them. This can be applied to any complex expression. So before we had the 5 + 8, also we have to assign a meaning to 5, assign a meaning to 8, and assign a meaning to plus, which is giving us the rule to put 5 and 8 together and what that is supposed to return. So how can we use this in language, and can that help us? We would need 2 ingredients. We would need to know how to interpret each word, and we will see how we can do that using types. And we need to make sense of what is this order in which the words come in, and that's going to be our grammatical structure. How does this work? We then compose the interpretations of the words following grammar rules, and then we should have the interpretation of the more complex expression. In this example, we have this very simple constituent in English, and we have fluffy that gives me, that is a part of speech adjective, and dog, which is a part of speech noun. And this will give you a fluffy noun fluffy dog, that we will interpret as a noun. And this is because we should be able to use fluffy dog in a sentence in the same place that we can use dog. So when we go to interpreting these in a compositional way, what we will do, what Lambeck introduced in 58, is the following. So we're going to say that nouns and sentences are the building blocks of our language. And we will assign types that represent them, N and S respectively. Further, we will say that adjectives and verbs are these maps, this compositional glue. So they will take nouns to nouns. That's what the adjective is doing here. And they will do that in a directional manner. So an adjective in English will only receive a noun from its right. And this represents a transitive verb that will receive one noun from its left, one noun from its right. First one is the subject and then the object, and gives me back a sentence, something with that S, which we will usually interpret as a truth value. So the sentence is either true or not true. We see how this composes here, precisely what we have here. The adjective of type N over N composes with an N and gives me back something of type N. Here, exemplified with a little diagram, is what the composition is for a sentence with a transitive verb. Now that we have the types, we are interested in knowing how exactly do we assign elements to the specific words. And this is where the current statistical models can be really good, because their underlying mechanism is to assign vectors to words, to all words. So they're all at the same level. They don't have any functional representation on their own. Usually you will have vectors that represent words that are described in terms of vectors that represent other words. And this allows the words to be represented with respect to each other, and to have a very simple measure of how two words would be similar to one another just by calculating their angular distance. So we can assign vectors just to the nouns, and then assign maps that take vectors to vectors as our adjectives, for instance. That would be a matrix. So to do that, we define a full-blown noun space that has as its elements vectors that represent nouns, an adjective space that is tension between the noun space, between two noun spaces, where the matrices that represent adjectives live, and so on and so forth. And then in a particular case, we would have the vector of dog being a vector in this space. Once we define a basis, we can represent, we can expand the vector in it. Fluffy similarly, with this being the noun basis, and then we compose it with inner product to get the meaning of the final big expression. This then will be a vector in our noun space. For simple sentences, we'll have a vector across the dimensions of true and false. This is two-dimensional, but of course it could also be one-dimensional. Now when we go to our quantum mechanical interpretation. So these vectors these representations involve a lot of data. So if we could store it more cheaply, that would be a great breakthrough. So one initial step to do that is to encode our vectors as quantum mechanical states. Because in the future, we hope that quantum computers will be able to hold huge amounts of information for much less hardware requirements. So this is how we would represent that. And then complex types will live in multipartite Hilbert spaces, and there'll be composite systems. And this scales up as well. And what further we can do is to, instead of just staying with states, we go to these density matrix states, which are essentially the same as quantum mechanical states, but they also accommodate for the possibility of having classical distributions. Quantum states only allow for quantum distributions, and density matrices allow for classical distributions as well. And this scales as before, and to compose them, we take the partial trace. And we have a final representation in the same space where we're representing our knots. What we have introduced is a way of distinguishing at the component of these matrices, at the level of these components, whether a function is waiting for an argument on its left or on its right by introducing raised and lowered indices. And the contraction then happens when we have upper and lower indices. And this is quite useful because the way in which we do this is by allowing that the underlying vector space is not just flat as it usually is taken to be, but it could also have a more complex topology. We are now in the process of getting experimental results on this. Okay, now finally I want to introduce you to this linguistic phenomenon, which is ambiguity in the reading. And so this case, man that bites the dog and man that the dog bites is translated to the same surface form in Dutch. Man die de hond bite. And why is this? Because bite in this final sentence position is expecting a noun, two nouns to the left. So we can contract either with dog or with man. And funny enough, when we ask Google Translator to translate back, it hasn't stored that original information. So it translates to the first reading. How can we keep that information in? So we see, in fact, what is happening is that this contraction is either happening already with the horns, or it can happen first with D and only then with the horns. And to control this permutation of contractions, a new type has to be introduced, and that is marked types with control modalities. So the type of D will be something that will have this funny diamond and box, and this will allow us to use extra grammar rules or hidden grammar rules that are not very obvious in our daily lives, but that they are there. So this is also very interesting because it allows us to create all this work in the logic of language that has been on the works for some time. So to store these two readings, or the fact that we can have two readings for the surface form in Dutch, what we do is, sorry, my alarm went off. What we do is we need to tensor our previous vector space with another spin space, in which we have a spin operation on a qubit acting as a mirror for our grammar rules as well. So different rules, but still rules that follow that. And in the end, what we have is the tensoring between what we get from our distributional readings, our directional density matrices, tensor with orthogonal states in the spin space. So now if a computer would look at this form, it would know right away that this has been derived using one derivation, and this has been derived using the other derivation. Thank you.
Thank you very much, Adriana, for your very interesting talk. Are there any questions to the speaker? Okay. Adriana, how difficult is this procedure of putting this quantum idea in the analysis? How complex it is?
Quite. So there's many levels of complexity actually. So one is to translate these words into these types and working at the logics level to have all the types put together in the right way and make sure that this is a well-formed fragment of language, right? And then on that, you have to interpret each word with a certain state, and then you have to interpret each grammar rule with a certain interaction between these spin states, right? That gives you something that that makes sense and that you can profit of. So the earlier incarnation of this is to just translate the vectors that come from the distributional models and just put them together in a very maybe naive tensor contraction. But now if you really want to go quantum and you want to do an actual quantum computation, for instance, you need to restrict yourself to a certain set of operations, and that can also be fun. And maybe we need to deviate a little bit from the pure logic of language to do other logics just with quantum computation.
Thank you very much. Is there any other question? Okay, so I think this was the last talk. So thank you very much for the presenters for their interesting presentations and inspiring, and all the attendees for their presence in the session. There is a kind of break where you can meet other people also around, virtually, but okay. So thank you again, and see you perhaps somewhere around or next time in real life. Thank you very much.
Thank you.